Okay, let's continue. Okay, today our objective is to conclude chapter 10. Okay, then next week we can do a little bit revision or discussion on your test 1 results. Okay, so today we continue on the eco-strain condition, where you look at the modulus equal to E fiber volume fiber plus modulus Young matrix multiplied by volume matrix. Okay, so for composite, it's very easy. You only have 2 components, A plus B equals C, or you can write fiber plus matrix equal composite. So you calculate how many fiber, how many matrix, then you get the total things lah. Okay, then you derive the equation. If you use the ratio loads, ratio loads mean you compare fiber with matrix. Then you use the Hooke's law or the definition of force. Force equal to stress multiplied by A, right? For stress equal to force divided by area. So you expand force equal to stress area. Same with fiber, same with matrix. Matrix is like a plastic lah. Okay. Fiber is like a rope. Then you expand the Hooke's law. By using Hooke's law, what is Hooke's law? Stress equal to E strain. Okay. So you expand the stress equal to E strain, modulus and strain, and you copy the area. Same with the fiber, same with the matrix. Then you know that the strain for fiber and matrix is the same in isostrain condition. Isostrain means the way you pull is balanced, right? So you can cancel the strain. The deformation of fiber and matrix is the same, so you can cancel. Then it left out modulus and the area. And because of the length of the fiber is the same, the length of the final product is the same, you can equalize, you can equal A equal to velocity. Okay, so you want to get velocity, this is the A, this is the L, or you can okay. So since you're going to get an A, the L is the same, right? L is the same. For example, you have a 2-layer. This is fiber, this is matrix. Then the L is the same. So you can equal area equal to velocity. Okay. So next we're going to apply this equation and this equation in the example. So you'll be seeing in your coming test or final exam, especially for chapter 10 question composite, you won't see any diagram. You don't see any picture. There's only a statement, right? So this example, you need to calculate the modulus of elasticity or E, the capital E, or modulus Young. Then tensile strength. Tensile strength is the maximum strength that you have, or UTS. The fraction of load carried by the fraction of load carried by fiber for the following composite stress under isostrain condition. So composite consists of what? Consists of glass fiber reinforced epoxy resin. So you have to identify which one is fiber, which one is your matrix. Okay. So here you know that it's a glass fiber, and your matrix is epoxy resin. You have to identify. You only have two main components. Composite, you have fiber and matrix. So this question, it gives you a composite consists of something fiber. This one is glass fiber. Then beside fiber, the next one will be the matrix. Your matrix will be epoxy resin. Produced by using, it gives you volume, 60% by volume of glass fiber, having a modulus elasticity, so it gives you a EF equal to something, and the tensile strength is something, and a hardened epoxy, this is a matrix, have a modulus something, and tensile strength something. Okay. So the question asks you to find the composite E, the combination between the two fiber and matrix. There will be one final properties, which is modulus Young or modulus of elasticity E, tensile strength, because here it gives you also tensile strength. So you just use the ratio between the fiber and matrix. You combine two together, you get the tensile strength. Fraction of load, does it mention load? Okay, fraction of load, fraction of load is just divide like the fiber and the matrix, what are their ratio, okay? So the first one, so straight away, again, the derivation, you can refer to the previous slides. So E equal to EF EV plus EV for matrix. So we have two components. Again, composite, you have fiber and matrix. So you just take the modulus Young for fiber multiplied by the volume. Or if the question changed to area, then you use area. Okay. So if the question give you area, you just change the volume into area. It's still the same. Okay. So you have EF, you have VF. Do you have? You don't have VF. So you need to find. Okay. Before you move forward, VF and VM, VF plus VM equal to 1. Because it's a one thing. So there's a fraction of volume for fiber and there's a fraction of for matrix. So you have to know. VF and VM, they just a ratio or there's the thing. So for example, these are the fiber matrix. So let's say you have 0.6 fiber. The another one will be have 0.4 the matrix. EF is the modulus Young, the Hooke's law. Stress equal to modulus Young and strain, correct? So the E is the modulus Young, or in this case, it gives you the elasticity. It's the same thing. Okay, modulus Young means you pull it, then you can let go, it can come back to its original shape. Elastic properties still there. Okay, composite, you have what? You have fiber and matrix. So you only deal with two things only. A very easy question, especially come to composite. All right, so you just include all the parameter you have in the question. Again, the only concept here is you have to understand the different the relationship between fiber and matrix, especially on the volume. You combine, you'll get 1. Okay, here it gives you the fraction already, right? Now it gives you 60%. 60% of fiber means if you draw a diagram, your fiber is 60%. So matrix will be 40%. Okay, so you change the percentage into fraction, into 0 point something. Okay, if 100% means 1. Okay, so here 60% you change to 0.6. Then matrix is another one, 0.4. Although the question do not tell you what is the matrix percentage, you should know that you should get 100% when you combine volume of fiber plus volume of matrix. Okay, so only I need to highlight here is the unit that you use. So here is 10 power 6. This is a tutorial question. In the assessment, we won't be so kind. We'll give you gigapascal, we'll give you megapascal, right? Or kilopascal. So you need to change to 10 power something correctly. So at the end, you get E of the composite is 6 point something. Typo error here, it's not 220, it's 10. Okay. 10 power something. Okay, again, when you do your assignment, please check your answer because some of my slides I have a typo error. Don't blindly copy. Okay. So I just put in a note there. If question asks for E modulus elastic in longitudinal direction, then you can use this to calculate. Right? You know that you can pull object in two directions, right? So if it's in the axial or along the length, this is longitudinal direction. Longitudinal. Right? And there are some changes in lateral direction also. But this one is usually to find the deformation. Okay. So here you find E equal to F by A. Sorry, E equal to stress divided by strain by Hooke's law. Hooke's law. Again, what is Hooke's law? Stress equal to E exponent modulus Young times the strain. Okay, so this is a very important formula. You write this one in, you will get 1 point or 1 marks in the answer. Okay. 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 So just a highlight here. If the question mentions something parallel direction, then it also means that it's a longitudinal question. Okay. If the question say that the forces is acting on a longitudinal direction, then you can use Hooke's law to calculate the force applied to that one. Okay. Then or the transverse travel in a perpendicular direction. Transverse is lateral direction. This is 90 degree. Okay. So you know when you pull, this one will go in one. Lateral will decrease one. Okay. Because it's elastic You pulling rubber, the diameter will shrink one. Okay. Okay. So typically, if you calculate the EC or modulus Young or modulus of elasticity for composite, you can use it to solve longitudinal problem. Okay, like what are the force acting on this area? Okay, what is the force acting on this area? Okay, of course it won't be cylindrical lah. You know, composite is sandwiches. Okay. Okay, we have done the A. What about B? B also same. B also same. The composite will equal to the fraction of fiber plus matrix. But here you use sigma V. You use sigma because it asks you about tensile strength. So you just use sigma. All right. Sigma, you know VC, composite is 1. Fraction is 1. So that's why you can use this equation. So composite will equal to fiber plus matrix. So stress of fiber already given in the question. Volume, you can read the question. You use the fraction. Fiber is 60%, change to 0.6. So Vm will be 0.4 automatically. This one also sigma matrix also, or the plastic also given in the question. So I think the only careless mistakes here, maybe you forget what is VC. VC is 1. Okay, just bracket write 1. Okay, so you just substitute all the value. You should also get the question. Quite direct, this composite question. It's very direct. Okay. No complex calculation. Okay. Then C, fraction of load carried by the fiber. It asks you about fiber. So you write force fiber divided by force matrix. Again, what is force? Force is E divided by, there's a derivation just now, so I just simplified. to the last one. So F equal to EV. The top one is fiber divided by matrix, right? So before we discuss example part, I show you the slide. So this one is a simplified steps. Okay. So in the assessment, in the test or final exam, please derive the steps. Okay. Just in case you memorize the wrong equation. But if you are confident, then okay, you can like do the same thing. But again, you know that we won't recycle the question in the lecture. So it's better you try to derive the equation that I show in the slides just now, because when you derive, you'll see that actually we designed a question based on that equation. So there will be something missing in that part, that equation. Okay. Okay. Then there is you can change the equation below into this equation. So so there is a derivation. There's a derivation. You know that the fraction carried by fiber is this one. So how to calculate FC? FC is actually FC again. FC is actually I do not write the full equation. So you always have I just write a normal parameter. P the parameter for composite multiplied by the volume of composite will equal to parameter of fiber times the fiber volume plus P of matrix plus volume of matrix. So P, it can be force, it can be stress, it can be any parameter. It can be strain also if you want. Okay, so the simple mathematics principle here is that the composite must combine with a fraction of fiber plus a fraction of matrix. Okay, so here, if you look at the slide here, if we under isostrain, then the bottom one I compare with the composite. Actually here, if you want to write V also can. V part, V is 1, so you cancel out the 1, right? So fraction of fiber plus fraction of matrix. Then you substitute the value, you will get 0.7. Okay. All right. Now, the force of composite will be 1. Because perfect case, the total force acting on the composite will be 1. This is like volume. Right, like 100% forces will be acting on the composite. So actually, bottom one here is 1. Make sense? Make sense? Cannot. Cannot. Okay. All right. So this one need time to do a little bit thinking. Okay. But still, it cannot run away from the fundamental one like this one. Okay. You still cannot run away from this one. Okay. So if you look at the question C, the fraction of load carried by fiber, you just compare, you just bring something that give you 1 at the bottom. Like fraction, it means something divided by something. So in this case, it asks you about force. Load is force. So force divided by the total force. Okay. Then the derivation is these slides. The derivation is here. Okay. So you can change below one. If the question asks you fiber and matrix, then you use this equation. Like the question in the tutorial just now, it asks you the fraction of load acting by the fiber or field by the fiber. Then this one you straight away use composite. Then this one become 1. all value here is 1, 1, 1, 1, 1 already. Okay. All right. We have done for composite, and this one is a very important slides. It's important for your test too. Okay. So we start to dissect go deep a little bit on the calculation. So what mean by iso stress? Just now it's iso strain. It's a bit different. The word iso strain, wait. Okay. Iso strain, the word is linked to deformation. The deformation in all the axes is the same. So you can use this equation. Okay. But what about isostress? When you have isostress and you have this setup, for example, so you have one layer of fiber continue with matrix, fiber, matrix, fiber, matrix, and then you have loading stress at both ends, so it's pulling both ends, so you're having tensile loading. So tensile loading, and you have an area, and you have a length of a composite. So let's say this is a complete composite, right? So the stress of the total composite will equal the stress feel by the whole body composite will equal to the stress feel by the fiber and feel by the matrix will be the same. Okay, because they are glued together. So when you pull them both ends, fiber matrix feel the same. Right? Means the stress acting on it will be the same. And this one is under isostress. Isostress. Okay. So total strain for the composite in the direction of stress, the total strain, total deformation in the direction of the picture here will be equal to the deformation of fiber plus deformation of matrix. This is isostress condition. Okay, let me show you the isostrain slides. The diagram of isostrain. This is the diagram for isostrain. It's different. This one is like this. Isostrain. Isostress is flip one. So isostrain, your LC is the same. So that's why when you pull the stress, so here stress is the same. So that's why you can do the ratio just now. Yeah. So that's why when you pull at both ends in isostrain, the deformation is the same. The deformation is the same. For fiber, matrix, everything is the same. If you pull at this one. But if you flip the object in isostress, then it will be different already. Okay, so you see, if you have this orientation, so if you have isostress, means you have the stress is perpendicular to the surface, then fiber and matrix, they have a different characteristics, so the deformation will be different. So the total deformation by the composite will equal to the deformation of fiber plus deformation of matrix. Okay, but the stress is the same. Stress is the same in isostress. The stress is the same. So if we assume the area perpendicular to the stress does not change, means this area do not change. The deformation here is the layer of that particular fiber and matrix. Right? So you can use the fraction again. Okay, you can use the fraction. This one might be simplified for you again. In this case, you change this one to strain. So actually, beside the composite, there's a bracket of volume of composite. This one, volume of composite always equal 1. Okay, so that's why you might see why suddenly there's no V on the left hand side. Actually there is, but we just simplify it. It's 1. Then VF, it depends on the question. It'll give you like just now, 60%, then 0.6. Then the matrix will be 1 minus the fiber volume fraction. Okay. So if you derive the equation and you recall Hooke's law, again, what is the Hooke's law? Stress equal to capital E strain. So you change the strain for fiber. Strain equal to what? So if you want to focus on strain, you pull the E to the left-hand side. So you get stress divided by E, stress divided by E, and so on. So this one will change, the strain of fiber will change to stress divided by EF. Because in this case, we are in iso stress, so all the stress will be the same, right? So it will change to yellow color stress, like you see on the screen here. Then we get the second equation. This is stress versus modulus Young equation, but it's still same. Composite on the left-hand side equal fiber plus matrix. Okay. So we substitute into 1. This is, this is 1. This is 1. Then you dividing by you take away you factor out all the stress because stress is the same. So you can cancel all the stress. So you get 1 over E composite equal to V divided by E fiber plus V divided by E matrix. This is for iso stress condition. So in your test next week, read carefully, either it's an iso stress or iso strain condition. Read carefully. All right. Okay. So this is fiber and matrix. Fiber and matrix. So again, you can change the fiber into matrix denominator. Okay, so this is mathematics, just mathematics. You can either focus on matrix or you focus on fiber. In this case, we change our, in this case, we modified. So for example, we put in the same denominator. The first one, EF, we change the same, the denominator is EF multiplied by EM. The second one, we take EM multiplied by EF, right? It's like you calculating the same, you want to get the same denominator in mathematics. For example, x equal to 1 over 4 plus 1 over 3. So how you get the common denominator is the first one you multiply by 3, 3 over 3 plus 1 over 3 multiplied by 4 over 4. Same concept in the mathematics. Okay. So here, if you multiply already, you get EF, EM, and so on. So as you can see, this is fraction volume for fiber, E for matrix plus volume of matrix plus modulus Young for fiber divided by modulus Young fiber and matrix. Okay. And you can further simplify lah. Okay, you can further simplify into the one that you see. Means you flip the equation. You flip the equation, you'll get this one. Okay. Because normally the question will give you the composite Young modulus or modulus of elasticity, or it asks you to find the modulus of the composite. So this is, you can memorize this one. We won't ask you the derivation steps. So if it is an iso stress, you use this equation. So there are 2 sets of equation. You try to identify whether it's iso stress or iso strain. 2 different equation. Okay. All right. Yeah. So this one again, I put a highlight there. Normally, where you see this equation if the question asks for E modulus elastic in the transverse direction. Transverse direction, then you use this one. Okay. If the question asks you E modulus in longitudinal, then you use isostrain. That is a different. Okay. So yeah. So this is how you know the question asking you it is isostress or isostrain. If it asks you to find modulus Young elastic in transverse direction, then use this one. If the question asks you in longitudinal direction, then use the isostrain equation. Okay. Right. So if you plot graph for the V fraction of fiber or VF versus tensile elastic E, so you will see EF and EM, you see in isostrain, you see a straight line. But isostress, you see a curved line. Okay. So again, isostrain, isostress comparison, direct comparison. So isostrain, you see the arrangement of fiber and matrix and the stress direction. Isostress, area and the stress direction. Okay, so as you can see here, this is a linear equation. It's a linear equation. So if you change fiber, y equal, this is y equal to mx plus c, because your x is volume fraction fiber, VF. This is your x. Y equal to mx plus c. So if you're given the equation of the graph, you should be able to find the missing parameter here. Yeah. So if you're given a graph or you're given a equation, a relationship between tensile of the composite and the volume fraction, remember there is a y equal to ms plus c equation that you can use. This is a linear equation for isostrain. However, for isostress, you cannot. Isostress, you have a parabolic equation. Okay, cannot. This is a parabolic one. Okay, so you have to use this equation. Okay, so this is additional notes lah. So I compare. This is a simplified diagram. So additional notes is that I changed the graph into a real scenario, which is the tungsten concentration volume percentage. So you can see upper bound and lower bound of the tungsten. Okay, so this one is the copper matrix with tungsten fiber. So you can see red one is the isostrain, blue color one is the isostress. So when you buy composite, normally they will show you these experiment properties. They'll give you that material chart. Okay, so they will show you the upper bound and lower bound. Okay, this one will guide you on how you place your sensor. Because if you want to place sensor on the vessel, on the container, you have to know the orientation of your composite. Right? You are not detecting. Make sure your value is within here and not outside here. Okay. Yeah. Again, just highlight just summarize the important point for you guys in these slides. All right. So this I think is a summary of important point. Okay. Okay. Let's apply what we learned again on composite. Again, no picture that you can see. It's just a statement, and then you find something. So calculate modulus of elastic E. For composite material consists of 60%, again, fiber and epoxy, it gives you 60-40. So again, volume, this one is volume. So you have your VF and VM. VF in this statement here is 0.6, VM will be 0.4. Under stress, when stress under isostress condition, this one very specific, is under isostress. So it'll be helpful if you can sketch or draw out what is isostress or isostrain condition. right? So the material stress perpendicular to the continuous fiber, modulus elastic E was given, the fiber was given, epoxy also given. In this case, give you megapascal, megapascal. So it asks you to find modulus of elasticity. So you just use the equation. Okay, just apply the equation, put in all the info, you get the answer. Okay, very direct. Okay. Because this is tutorial question, try to think how we re-engineer. So normally we will give you the composite final value. Then we ask you the volume or the missing piece. Okay. Then it tell you already isostress. Stress under isostress condition. Tell you already. Okay. Okay. So again, if it asks you to find modulus in transverse direction, also same equation. Although this question do not mention anything about transverse, but if you see this statement in the test 2 or final exam, then you know lah, this is the equation we're looking for. Okay. Okay. The rest is a fabrication process. I'll go very fast on here. Too bad we don't have a composite lab here. All right. Basically, what you need a mold. You need fiber and resin. Okay, you need fiber and resin, you pour in, and then let it cool down. Okay. Okay, the rest you read lah. These are all the process. So application will be many lah, composite, right? Boat, cars, aircraft, all these things. So you have a coating, again mold, and then some reinforcement there. Okay, this one is by hand lay process, meaning you do it manually. You brush the fiber and matrix together, you brush it. Okay, this is hand laying. Another one is spray. This one is a more automated process where you use spray process. You just mix all the component, all the resin, and then you spray to the surface. Just now is you use roller, then another one you use spray. Okay. Okay, I'll show you some video. These are people doing boat lah. So you see this person outside here is spraying. Then the back one is doing lowering. It's just to get the things done. So there are two processes. Normally, when you do this one, if you are the safety officer or OSHA, occupation OSHA, this video fail because this worker do not wear mask. Okay, they do not wear mask. It's actually a hazard, very hazard material, right? Okay, another one is autoclave process, which is more industrial things, most automotive parts lah, like the body parts and all this, right? So you use a vacuum bag to vacuum it lah. Okay. This is also use vacuum lah. You just squeeze everything in and then you let it cure. Okay. This is a picture inside the autoclave process. This is what? Vacuum backing material. Okay. So I show you like how to do the vacuum back autoclave process. We prepared a sample. This is a mold release. This is another, the first layer, laminate. This is another layer. This is another side is to make the surface very smooth. One additional cleanup. You clean up because later the process is using vacuum. So if it's not clean, then you might dirty make the products not very nice. So you want to tape the surface again, seal off the surface. This another layer. Then one more sealant tape. Clean the surface again. The jump step a bit. You just seal off and then vacuum the thing. Then put into the autoclave machine, the heating machine. Okay. Okay. Huh? No, just give you the how vacuum bag autoclave process. So at least you heard before what is autoclave, how to do all these things. Okay, another one is film winding. This one is very common nowadays. We use machine to rotate the thing, right? Filament winding, this is more industrial. Nowadays, you get all this process. Okay, something like this. Filament winding. It's like making wires, all this. Okay, so it will this one will rotate, then it will move so that the composite layer will be there. Okay. Compressed injection molding, this one you know already. This one you watch after the class. Injection molding is the same. CNC, CMC, SMC process, sheet molding compound. Sheet means the form is a thin sheet. This one you read. Okay. This one I can show you. This is a sheet molding compound CMC process. So the fiber was chopped to small string. And don't go and touch fiberglass. You will feel itchy. Your hand will feel itchy. Right? So you have to protect both sides with plastic so that you don't touch it and then feel itchy. So when you buy fiberglass fiber, you come in roll plastic. Okay. Then continuous protrusion is a long process, right? Long process. Yeah, this one you watch, you watch at home. Okay, important is a metal matrix composite. When you go out to work later, maybe you will see this one, where you combine metal inside the matrix, okay, for conductivity or so on. So you have a continuous long fiber, something like this. You have discontinuous short fiber, and you have particles in matrix, something like this. So there's a different kind of reinforcement. Okay, so these are the reinforcement for composite. Whether you use fiber, discontinuous fiber, or particulate reinforced. These are the properties, right? What are the composite name and the properties here? This one. So also there are some parameters here. Okay. We need to go into crack propagation. Crack propagation, you have a crack diffraction. You have a crack bridging. So the first, we call it defect here. For crack diffraction is you deflect the with reinforcement, then the crack will be deflected. So make the propagating part more mindering. So you can handle more stress. Second one is crack bridging. Crack bridging is for the fiber. The fiber can bridge the crack and help keep the material together. So these are the benefit of CMC, the ceramic matrix composite. Fiber pull out and so on. So I don't ask you this one. Okay, so this is an important example. Let me check. Okay, I think we have a short break. Then we continue with example 7. Okay, we have a short break. We continue 3:10.